Welcome to our fifth video on NMR. In this video, we'll be focusing on NMR of carbon atoms rather than hydrogen atoms. And at the end of this video, we'll follow up with a small vignette on some advanced topics in chemical shift analysis for all types of NMR, but focusing on protons. So let's deal with what's called carbon NMR first. This is an example of heteronuclear NMR, which describes any technique where we're looking at atoms other than hydrogen. So I'm going to draw your attention to a table that I showed you in the first video when we dealt with NMR physics, and that's this concept of our spin number. So in that video, you could see that carbon-12 has a spin number of 0, which is a problem because that means that carbon-12 atoms are essentially invisible to NMR. But an isotope of carbon, carbon-13, actually has a spin number that's not 0 and is therefore visible to NMR. The issue here is that carbon-13 is only about 1% of all of the carbon atoms on Earth, so our signal is very weak, and that causes a few different kinds of problems for interpreting and acquiring NMR data for carbons. First of all, we have to actually have much longer techniques. So the total time to acquire a proton NMR spectrum is about 5 minutes in front of the instrument, whereas a carbon NMR would take anywhere between 1 and 3 hours. We also need to acquire a larger number of scans, or basically we're going to make the measurement thousands of times for carbon NMR, whereas for a proton NMR we might make it 8 times in order to reduce random noise in our measurements. But there are other issues also. So I'm going to show you here the carbon NMR of toluene or methylbenzene, a structure we've seen before, and you'll notice a few things looking at this this expansion of a carbon NMR spectrum, and that's first, the peaks are very complicated. These don't look like doublets or triplets or singlets. They look like, well, I don't even know how to describe them. Lots of lines, unmown grass maybe. And you could imagine, would be very difficult to gain any type of structural information from this kind of a spectrum, at least with respect to coupling. The other thing you'll notice if you're careful and you look at the x-axis is that the numbers look really different. These are much larger values of chemical shifts than we saw for proton NMR. So we need to do a few things to actually acquire useful information with carbon. And the first of those is to actually turn off all coupling or splitting. So we would end up with a spectrum for the same compound that looks like this instead. So what we've done is actually zoomed out. This is the total carbon NMR spectrum for toluene. You'll notice the x-axis range is much, much bigger than you would otherwise expect. We go from about 0 ppm to 200 or even a little bit higher. And what we're doing is basically setting up the instrument in such a way where there is no coupling allowed. We get single signals or singlets for every unique carbon atom. The other thing that I want to note here, when you look at these signals, is that all the heights or intensities, I suppose, or areas under the peaks, they're all different. And that's because integration in a carbon NMR spectrum doesn't really have physical meaning that we can use unless you set up the instrument in a very specific way, which takes much, much longer even than the 1 to 3 hours I quoted you earlier in the video. So really, for the most part, carbon NMR is a much more limited technique than proton NMR in that we only have 2 pieces of information that we really want to focus on. We can determine chemical environments for carbons only using chemical shift and the number of signals that are present in the carbon NMR spectrum, because we know that latter characteristic will correspond to the number of unique carbons or non-equivalent carbons in a molecule. So I'm showing you the structure of 2-butanol here, along with its carbon NMR spectrum. And so I thought what we could do is actually assign carbons to signals to get us started with how we would use chemical shift. Well, it turns out the chemical shift in carbon NMR works the exact same way as it does with proton NMR. For the most part, we're looking at electron density. So carbons that are more electron-rich will have smaller chemical shifts or be upfield or to the right in our spectrum. And carbons that are less electron-rich will be downfield, have larger chemical shift values, and be to the left in our carbon NMR spectrum. So when we go to assign, it's usually helpful to assign letters or numbers to the carbons. Every carbon in this structure is unique. There's no symmetry here. None of the carbons exist in equivalent environments. So we should see 4 signals, and that's what we do. We actually see the same number of signals as we do unique carbons. That's good. And so what we can do now is assign these. I'd like for you to take a stab at just assigning where carbon-3 is in the structure. Where it is in the spectrum. It's given to you in the structure. So which signal in our carbon NMR spectrum comes from carbon-3, and also which signal in this spectrum comes from carbon 1. So please just assign carbons 1 and carbon 3 to signals. Pause your video and do that now. So if you think this through with using electron density, you might assume that the peak that's furthest downfield, so the signal with a chemical shift of about 70, would be carbon 3. And carbon 1, being the furthest away from the oxygen, would be the most upfield, so that would be the signal at around 10 ppm. And it turns out that you're right. But assigning carbon 2 and carbon 4 would be a little bit more challenging because they seem to be kind of like the same distance away from the oxygen. And now we're trying to decide, like, well, carbon 4 has 3 hydrogens attached, carbon 2 has a carbon-carbon bond that carbon 4 doesn't have. So, like, those differences aren't going to be easy for us to parse, but it turns out that there's a general rule here, that as the substitution at carbon goes up, so does the C13 NMR chemical shift. So you can see the total assignments here on the spectrum. And so this is, like I said, this is a general result, right? Typically, if you look at a carbon that has like 3 other carbons attached, that carbon will have a higher chemical shift than a carbon that would be very similar except for only having like 1 carbon attached. So when we talk about substitution, we mean kind of like how you thought about carbocation stability in the first semester of organic chemistry. Like a tertiary carbocation is more highly substituted and therefore is more stable. I want to be clear. The rationale for that carbocation stability is not the same as it is for the chemical shift features that you see here, but you can remember those rules as being kind of equivalent. Okay, so to parse chemical shifts, we'll use regions just like we did for proton NMR. And it turns out that'll be pretty much the best thing you can do with carbon NMR data, at least in this class. Although again, like many other things we've talked about in this unit, if you end up going on to do organic chemistry in a research or professional capacity, or if you use NMR in a biochemical context, there are many, many, many powerful techniques where carbon NMR can be much more useful and much more detailed than how we'll treat it. So just a caveat. So I'm going to show you the regions for the carbon NMR spectrum with respect to shifts. And this spectrum is of the compound you see on the slide. So you can see a lot of different functional groups, a lot of different types of carbons, and that's going to be helpful for us to actually sort these regions. So we'll work left to right. From about 210 to about 160 ppm, these are going to be carbonyls. These are the carbons that have a double bond to oxygen. And as you know, hopefully, when you've talked about functional groups, there are a lot of different kinds of carbonyls. So we have esters and amides and carboxylic acids. We'll talk a lot in kind of gory detail about these functional groups later in the semester. But for now, just know that carbonyls tend to be very electron-poor carbons, and so they're going to be quite downfield. Aromatic carbons are next. So these will fall anywhere between about 160 and about 110 ppm, although there are exceptions where you can be outside of this range on either side. And so these carbons will be from benzene rings or aromatic rings that aren't benzene, as you might have learned about last semester. You don't need to be a benzene ring to be aromatic. Alkenes fall at around 140 to 115 ppm, which overlaps substantially with the aromatic region. And that's partially because alkenes and aromatic rings are pretty similar with respect to the structures of carbon atoms. These are both sp2 hybridized. So it can be tricky to know whether you have alkenes or aromatics in your structure given a carbon NMR spectrum. You would typically need to use both what you find in the carbon NMR spectrum and what you find in a proton spectrum or potentially IR to know whether or not you have an alkene or an aromatic ring. Although, as we'll see later in this video, there are inferential techniques that you can use also in some cases. So moving further upfield, we have functional groups that carbons that are attached to functional groups. So another way of saying that is carbons that are directly bonded to an inductive acceptor group. So you can see the carbon of our ester here. That carbon that's directly attached to an oxygen is going to be feeling a very, very powerful inductive accepting effect from the oxygen because there's just the one bond between them, right? So we've got this direct polarization. So depending on the number of these withdrawing groups and the electronegativities of those atoms, you can be within this kind of large range for carbon NMR. But what's helpful here is that we can distinguish carbons that are attached to these kinds of atoms from carbons that are not. So carbons that are simple alkanes, really not attached to anything other than carbons and hydrogens, you're somewhere between about 40 and 0 ppm. So we can practice using regions in a way that I would like for you to encounter carbon NMR data, and that's to use it a little bit like IR. We can't assign a whole structure to a compound using just its carbon NMR spectrum typically, but we can work out pieces of a molecule, so maybe like a functional group or whether there's an aromatic ring or not. So these structural features we can infer and then use those essentially like puzzle pieces to either reinforce what we think we have using from a proton NMR spectrum or in using some other kind of spectroscopy to help us stitch together these individual pieces that we can observe in carbon NMR. So to do that, we'll use our regions, and in this case, let's work from the lowest chemical shift values or the upfield part of the spectrum, and then we'll work to our left. So we see that looking in the region between 0 and 40 ppm, we have one simple alkane carbon. So this is like one carbon that's probably not attached to any oxygens or nitrogens or fluorines or whatever. You can see it's right at the end of that region. So for an aliphatic or simple hydrocarbon carbon, this is a relatively electron poor C. We don't know why yet, but that's something to note. So we'll then move to our next region. So these are the carbons that are directly attached to elements like fluorine, oxygen, nitrogen, or a halogen. And we see we have two of these. So we have two distinct signals in this region. That means we've got two different carbons that are attached to fluorine, oxygen, nitrogen, or halogens. We need to be clear that we don't know how many of those non-carbon groups we have. So we could have two fluorine atoms. We could have one oxygen that both of these carbons are attached to. We don't know. We just know that we have two different carbons attached to an element of that kind. We also don't know which kind of element it is. We don't know if it's a fluorine or an oxygen or a nitrogen. So moving up into our alkane, our alkene and our aromatic region, we can see we have a few different signals here. I'm counting 4. And I'm showing you the overlap for the alkene and the aromatic region. You can see it's pretty substantial. So right now, all we could say is that we either have alkenes and or aromatic rings. We don't know which one yet. But we can actually do a little bit of inference here. We can count the number of signals within this combined region of about 160 to about 110 ppm. And so if we know that alkenes require us to have 2 carbons, we're going to be able to count in multiples of 2. So if I have 4 signals, either I have 2 alkenes or I have an aromatic ring that has 4 unique carbons. That's going to be consistent with an aromatic ring that has one plane of internal mirror symmetry or a symmetrical aromatic ring. So those are both possibilities. If you count 4 signals in the aromatic region, more times than not, this is an aromatic ring with a plane of symmetry, but it doesn't have to be, right? So we can't be conclusive here, but if it were me, I would hedge more toward a compound that contains an aromatic ring given this spectrum. And then finally, we can see that there is a signal in the carbonyl region, but we don't know what kind of carbonyl yet. And again, here we can use chemical shift reference information to have a good idea about what kind of carbonyl functional group is present in the structure. And that carbonyl or ketone carbons come at about 200 ppm. So this is definitely not a ketone. We're way outside that part. Aldehydes come at around 190, so it's highly unlikely the carbonyl in this structure has an aldehyde. On the other hand, esters and carboxylic acids have carbon NMR signals around 170 ppm. So that's pretty much smack dab on where the signal for our spectrum is showing up. And then finally, amides have signals at around 165 ppm. So I would say that if we had to pick one of these groups, it's probably an ester or a carboxylic acid. It could be some kind of an unusual amide. We don't know yet. So to resolve these two possibilities, an ester or an acid versus an amide, we would need to know something about the molecular formula of the compound. In particular, we'd look to see whether there are any nitrogens present. If not, we cannot have an amide, and all I'm left with is an ester or an acid functional group. So you can see that with carbon NMR, you can actually get quite a bit of structural information. It just doesn't look like the drawing of the structure. It looks like pieces of a structure. So when you encounter carbon NMR data, I would strongly encourage you to use it the way we've done it here, to actually write a list of the kinds of features that you can infer from the spectrum. And then if you have that list, it will help you when you go to look at proton NMR or IR data. All right, so let's switch up a little bit, and we're going to start talking about an advanced topic in assessing chemical shifts. And we'll focus on this in proton NMR, but it turns out that the same effect is relevant for all kinds of NMR. So I'm going to draw your attention to a structure we talked about in the second video in this unit, and that's this kind of benzene ring with a methyl group that has 2 chlorines instead of hydrogen. So we could call this like dichlorotoluene, for instance. So one of the things that I tried to wave my hands around when you were seeing this spectrum initially was why the signals in the aromatic region are so far downfield, right? That lump of signals that's integrated into 5 hydrogens around, let's say, 7.5 ppm, those are protons on the aromatic ring. But the protons on the hydrogen that's attached to the carbon where the chlorines are is actually upfield at that point. That doesn't make any sense. The hydrogen that's right next to those 2 chlorines should be far less electron rich than the hydrogens on the aromatic region or aromatic ring. So like, what gives? And it turns out that aromatics and basically any sp or sp2 hybridized carbon is influenced by a special kind of effect that doesn't have anything to do with a buildup or lack of electron density. These effects are called anisotropic effects. So they basically involve this concept of ring current. This is kind of a busy diagram, but the idea is that if we have something like a benzene ring, the electrons within that ring, they could in principle like move in a circle. So you can see these kind of blue donuts on the top and the bottom of the benzene ring, and that's where the electrons that are a part of the aromatic system essentially reside. So when you put those electrons in an external magnetic field, like inside of an instrument or an NMR instrument, they do actually move in a circle. But because they're charged and they're moving in a magnetic field, Lenz's law tells us that those electrons will create their own induced field. Because the electrons are moving in a circular fashion, they create these kind of circular-looking magnetic fields, which you can see with these darker green arrows. And those fields have a distinct direction that opposes the external magnetic field very strongly inside the ring. But for anything outside the benzene ring, so like where the hydrogens are attached, this induced magnetic field from the ring current dramatically adds to the external field. So another way of saying that is that the hydrogens on the outside of an aromatic ring have their effective magnetic fields, or BEFs, dramatically increased because of this unusual type of induced magnetic field that works for rings. And that pushes protons in the on aromatic rings way downfield, way further downfield than you would expect, given an electron density argument. So this is sometimes called anisotropy, and like I said, it comes from this concept of ring current. So, you know, if you're a skeptical person, which I would appreciate, you might look at this and say, this looks like bullshit. Like, how do we know that this is actually happening? That's a fantastic question. We could do an experiment, right? There's actually a couple of things we can predict here. And the one that we could predict that would be the most useful is this concept of what happens inside the ring. If I was somehow able to put a hydrogen atom inside the ring, its chemical shift should be tiny. It should be way upfield, because this induced magnetic field from the ring current is going to be dramatically fighting against the big magnetic field from the magnet itself. So you can't do that with a benzene ring. The ring's way too small. But you know that aromatic rings can be large. As long as they satisfy Huckel's rule, they count as aromatic. And so organic chemists made a structure that looks like this. This is called 18-aniline. And we can actually get protons inside the ring. So here we actually find that for these types of structures, the hydrogens inside the ring have chemical shifts of -3 ppm, which is tiny. It's some of the smallest chemical shifts measured for hydrogen atoms. So this seems to confirm this concept of ring current and anisotropy in NMR. We also see this effect in alkenes in a slightly different way. We don't necessarily have ring current anymore, but the presence of the pi bond gives us these kinds of cones where the groups that could be hydrogens, where those wedges and dashes are, have a similar effect. It's not as dramatic as in an aromatic ring, so the chemical shifts are going to be a little bit smaller. But that also explains why the alkene region is far downfield of what you would expect relative to an electron density argument. So finally, we can see that the same effect holds for alkynes, or specifically the hydrogen that points off of the end of an alkyne. And here the argument's reversed. In an alkyne, inside that cone, the anisotropic cone, the hydrogen is actually shielded by this, let's just call it magnetic field coming from ring current, even though that's not exactly accurate. So the alkyne chemical shift is a little bit low for what we would expect given like hybridization arguments or bond length arguments or electron density arguments. So this is a little bit like the hydrogen that was inside the ring of aniline, but again to a lesser extent because we're no longer dealing with the ring. So I just wanted to make sure that I addressed this concept where you were, you know, if you're thinking critically about your chemical shifts, you should have been concerned about why aromatic rings or protons on aromatic rings and protons on alkenes were so far downfield given how we were saying, well, chemical shifts are about electron density. they are about electron density, but when relevant, they're also about anisotropy. So when we have these pi bonds, the hydrogens directly attached to those carbons, for instance, they're going to feel this effect as well. All right, so that concludes our 5th video on NMR. In this video, we discussed carbon NMR, as well as the concept of anisotropy.